Does anybody have any questions? Finish up aromaticity, and aromaticity will be on Friday's exam. So I'll post a few practice problems on this. So on Friday we were talking about the two rules that make something aromatic. And again, aromatic means that it has super stability. It won't react under most conditions. And that is that all the atoms in the ring have to be sp2 hybridized. And then if that's the case, then we go to rule number 2, which says that you have to have a 4n plus 2 number of pi electrons. So that means 2, 6, 10, etc. in that series. And we looked at a couple of examples and expanded to say it could be aromatic, it could be non-aromatic, or it could be anti-aromatic. With anti-aromatic having all of the atoms sp2, but having a 4n numbers of electrons. So that's anti-aromatic. Now we want to expand our normal rings here to include things like what are called heterocyclic aromatics. So that's the next thing that we're going to take a look at. So when we go to something like a heterocyclic aromatic compound, we'll start with something like pyrrole as the example. And I'm going to come back to a blank page here. So, well, I was going to go to a blank page. So let's look at the before we look at a heterocyclic compound, we need to go back and we need to look at hybridization possibilities for things like nitrogen. So if you have a nitrogen with 3 bonds and a lone pair, what would we expect the hybridization of that nitrogen to be? We would expect it to be sp3 because the 3 bonds and the lone pair would be hybrid orbitals. And for the most part, that's the way the nitrogen starts out. And if it was in an sp3 hybridization, we would expect then our tetrahedral structure with then one of the lone pairs being in the hybrid orbital. But nitrogen doesn't have to do that. Nitrogen could decide to go into an sp2 hybridization. And if it did that, it would look like this. You would have your 3 hybrid orbitals, you'd have your 3 sp2 hybrid orbitals, and then you would have the lone pair in the unhybridized p. So nitrogen can choose to either be sp3 or sp2 hybridized. A carbon atom can do the same thing. And I should take a step back. This could happen with nitrogen. It could also happen with oxygen. Remember oxygen having 2 lone pairs, so it could put 1 lone pair into an unhybridized p orbital and another lone pair into the sp2 hybrid orbital, so oxygen can do that. Sulfur could do the same thing. For carbon, what we know is that a carbocation has to be sp2. So when you have a carbocation, it must be sp2. with an empty p orbital. But if you had a C minus, if you had a C with 3 bonds and a lone pair so that it has an overall minus charge, carbon can do the same thing that nitrogen does. Carbon could either be sp3 hybridized, where it would put its lone pair into an sp3 hybrid orbital, or carbon could put its lone pair into a p orbital, and the carbanion could go into an sp2 hybridized state. So this carbanion then can either go here or it can go here. I think up till about, for something simple like CH3 minus, I think it was only about 15 years ago maybe that somebody finally was able to determine that the CH3 minus was tetrahedral. But these atoms, we're going to give them the opportunity to choose. Again, treating them like with human characteristics. And what are they going to choose? They're going to choose to become sp2 hybridized when that will make all of the ring atoms sp2 hybridized, and when those 2 electrons or whatever number of electrons they put in the p orbital will then make the rest of the p orbitals, the number of electrons, equal 4n plus 2. So these atoms can choose to be sp2 when they can throw their 2 electrons into the pot and basically end up being 4n plus 2 pi electrons. So in other words, they're going to choose to be sp2 when they can make the system aromatic. And they will not choose to do this when the system would become anti-aromatic. Because as I said on Friday, there's not going to be, molecules will not deliberately choose if they have an option. They will not choose to be anti-aromatic. They would much rather just be non-aromatic and not super stable than to become anti-aromatic and super unstable. And we'll see examples of this. Okay. Right, so that's the possibilities in terms of heteroatoms, also in terms of carbons. So let's take a look then at these heteroatoms. And there's pyridine, pyrrole, furan, and with the sulfur analog, which is called thiophene. Let's take a look at pyrrole. So I'm just going to do this from scratch. So here's my pyrrole molecule. So as it stands, we've got 5 atoms in the ring. 4 of them are sp2 hybridized with the double bonds. And if nitrogen decides not to be sp2 hybridized, the system's non-aromatic. But what if nitrogen decides to become sp2 hybridized? Well, if it decides to become sp2 hybridized, rule number 1 is met. All the ring atoms are sp2 hybridized. And then what about the lone pair? Well, if I draw that structure out, kind of trying to draw it sideways, we've got, here's our p orbitals of our double bonds, right? So there's 2 pi electrons, there's another 2 pi electrons, so I've got 4. If the nitrogen decides to go sp2 hybridized, the hydrogen is going to be in the hybrid orbital, and it's going to have a p orbital with 2 electrons. And that p orbital then is going to be parallel to all the other p orbitals. didn't quite necessarily say this in the case of the benzene ring, but one of the things you see with aromaticity is, with all the atoms being sp2 hybridized, they all have their p orbitals parallel to each other. And what that does is that allows the electrons then to kind of delocalize in all of those p orbitals. It's similar to in the conjugated system. In the conjugated system, all of the all the p orbitals are parallel to each other, and this single bond is a little bit shorter, or has a little bit of double bond characteristic because of the partial overlap of those two orbitals. And so that's what makes a conjugated system more stable than an isolated one, is that all of these orbitals are actually parallel to each other. And then you have a partial overlap here of these orbitals that aren't involved in the pi bonds, but that causes the single bond then to become a little bit shorter. And I think this has always been accepted as the case, but I think one of the professors at Oberlin, who's now retired, although he's still around, he was the one, I think, within the last 10 years, actually, they did some infrared on this and were able to show that bond is actually shorter than a single bond. Up till that point, it was just accepted that was the case. There wasn't any real evidence of it. So we have to understand that with a pi system, all those p orbitals are going to be parallel and there's all going to be overlapping. So coming back to this one then, if the nitrogen can put its p orbital, then it'll partially overlap with the rest of the pi bonds, but now it's throwing in 2 electrons into the pi system. So how many electrons are there? There's now 6 pi electrons. So not only did the nitrogen fulfill rule number 1, which is all the atoms have to be sp2, but it now made the complete pi system with 6 pi electrons, which means that pyridine, or this pyrrole molecule, is aromatic. And so those double bonds in pyrrole will not react the way that a conjugated system will, or any other double bond. They're going to react more like benzene double bonds, which we'll get to in a couple weeks. So that's a case where nitrogen decides to go sp2 and it makes the system aromatic. If we go to something like pyridine here, pyridine is already sp2 hybridized because that nitrogen has 1, 2, 3. It has, well, according to Vesper rules, it would have 1, 2, 3 sets of electrons, so it would already be sp2 hybridized. So when the double bond is to the nitrogen, there's no question it's already aromatic. And then the pyridine, we've seen that the pyridine is also, or the pyrrole here, is aromatic as well. So both of these, well, all 4 of these are actually aromatic because the nitrogen is either sp2 or it chooses to be sp2. You could say, what about furan? Well, furan is also going to be aromatic because what its oxygen will decide to do is it'll decide to become sp2 hybridized as well. So the furan is going to look exactly like the pyrrole. We've got our 2 double bonds. Then the oxygen says, okay, if I become sp2 hybridized, then I can meet rule number 1. So I'm going to go ahead and put one lone pair into an sp2 hybrid orbital, and I'm going to put the other lone pair into an unhybridized p. And when I do that, now all the atoms are sp2 hybridized. They have that continuous overlap, and I've got 2, 4, 6. I've now got 6 pi electrons, so the system is now meets 4n plus 2. So that system is also aromatic. Everybody with me? And then you can, then in the PowerPoint notes, it kind of goes, it just gives you the more colorful pictures of that. Here's the nitrogen with its lone pair. Again, that lone pair is now parallel to all of the other p orbitals. And the oxygen, the same thing. This lone pair in the unhybridized p is going to be able to overlap with all the others. So heterocyclic compounds can become aromatic by a nitrogen or an oxygen choosing to become sp2 hybridized, but only if that pair of electrons then helps the overall system reach 4n plus 2. If it doesn't, it won't. Nicole?
Can you explain the 4n plus 2 rule?
So all the 4n plus 2 rule does is it generates a list of the numbers of pi electrons that will give you, that will make the system aromatic. So if I start with 0, I would get 2. So when n equals 0, I get a number 2. When n equals 1, I get 6. When n equals 2, I get 10. So all that 4n plus 2 rule does is it just generates the list of numbers of pi electrons that will make the system aromatic. That's all it does. So if you say, well, I've got 8, 8 doesn't fit 4n plus 2 because n has to be an integer. So if you solve 4n plus 2 equals 8, you would get n not being an integer, so therefore that's not an allowed value. 8 would equal 4n. And a system with 4n numbers of pi electrons is now anti-aromatic. So that's all the 4n plus rule does in this class. There's a fundamental reason for it, but we're not going to get into that. Okay. Anything else? So let's look at some. Let's see. Let's look at 2 examples, and I'll ask you. So, and again, I've got some practice problems. There's also another aspect to this that I will sort of talk about. So here's a molecule. Is this one aromatic, non-aromatic, or anti-aromatic? So for the first one, Walk me through how I should determine that.
Looking, make sure all the carbons are sp2 hybridized.
Okay, so all the atoms, are they sp2 hybridized? Which one's not?
The middle carbon.
Let's see, you've got 1, 2, 3. We've got 4 bonds, but we only have 3 sets. So actually, these two are sp2 hybridized because the carbon just has to have 3 sets of bonds. So it's got to have one double bond and one double bond and 2 singles. So this carbon has 1 double and 2 singles. This one up here has 1 double and 2 singles. So it actually would be sp2 hybridized. I guess all the ring atoms sp2 hybridized.
Everything is bypassed, that's the machine, and in this case it would just be sp2 hybridized.
Okay, so everything is, all the carbons are sp2 hybridized. And does everybody see with these two fusion points? Because that's the first time we've looked at, well, it's the second time we've looked at something like that. But as long as it's got a double and 2 singles, it will be sp2 hybridized. So the only thing that's really the question is nitrogen. So this nitrogen then, if it decides to become sp2 hybridized, it's going to have these 2 bonds and the hydrogen in the hybrid orbitals. It's been a while since we've talked about hybrid orbitals and hybridization. But remember that the only thing that can go into p orbitals is lone pairs. Lone pairs could go into hybrid orbitals as well, but a bond to an atom cannot go in a p orbital. Bonds to atoms can only go into hybrid orbitals. So this nitrogen then, if it decides to go sp2, these 3 are going to be then the hybrid orbitals, and what happens to the lone pair. The lone pair goes into the unhybridized p. And therefore it gets counted as part of the pi system. So how many pi electrons does this have before nitrogen? It's got 2, 4, 6, 8. And if nitrogen's pair now becomes part of the pi system, it's got 10 pi electrons. Does 10 obey Huckel's rule of 4n plus 2? Yes. So this system would be aromatic when the nitrogen decides to become sp2 hybridized, which it will, in order for the system to become aromatic and stable. Does everybody see that? I didn't get a chance on Friday to ask in this class. So now that we know this system's aromatic, does that look like anything that you might have talked about in your biology class or genetics or some non-chemistry class?
Is that a nitrogenous base?
Let's come back to that, whether it is basic or not. But does it kind of resemble anything? What? You nodded your head, Katie. Okay. So it looks kind of like a base pair in DNA. So It does resemble that, and if you go back and you look at those, I'll bet that's ATCG, right? I don't know. If I told you how much biology I took as an undergraduate, one class, second semester senior year, while I was taking biochemistry, it was bad for the freshmen in the bio class because they didn't get a curve. But it's okay. They survived. So when I say I know this much biology, usually my fingers are very close together. Also, I tend to sandbag people a lot, so I might know a little bit more than what I'm letting on. But if you're going to take these systems, if you were going to make a DNA molecule sort of base paired together with the hydrogen bonds, you'd want a rigid system that's flat. And you also want that inside that system to not react. So these aromatic systems would be perfect for that, because they're not going to react and they're going to be rigid to be able to form all the hydrogen bonding that you need to form a double helix of DNA. So you have kind of seen these before. You just haven't really talked about their organic reactivities. So this is aromatic. Now we'll talk about whether it's truly a base or not in a minute, because nobody's ever used that term, the nitrogenous base. So I might have to bust up about something they're telling you in biology, but that's okay. Let's look at this other one here, because I like to ask this question sort of as a thought-provoking question. So is the molecule on the right, is it aromatic? Or how would it be aromatic? Or could it become aromatic? So this system already has 4 pi electrons built into it, right? So what happens if this nitrogen becomes, what's going to happen for this system to even think about being aromatic? This is going to have to be sp2, and the oxygen is going to have to be sp2, right? First rule is make all of the ring atoms sp2 hybridized. So if this system is going to be aromatic, the nitrogen and the oxygen have to become sp2. But what happens then, Nicole? So in other words, if this nitrogen becomes sp2, we've now got 2, and if this oxygen was to become sp2, it would now throw in another 2, which would give us 8 pi electrons. So if this system was planar, it would have 8 pi electrons, which fits the 4n rule, which says that system would then be anti-aromatic. So if this molecule decided to become planar, it would become aromatic. But in order to do that, both the nitrogen and the oxygen have to choose to become sp2 hybridized. Will they do that? They won't deliberately choose to become super unstable. So one of the two may, but both cannot. So that means that this system is not going to become anti-aromatic because it has a choice. It's just going to basically be non-aromatic. It's going to be non-aromatic, and either nitrogen or oxygen will become sp2 hybridized just to overlap with the 2 pi bonds, or the two double bonds. But both of them can't. Now, which one, nitrogen or oxygen, I don't know. That's one of those things where we'd have to either make it and determine the structure, or better yet, model it on the computer to try and figure out which of the two atoms would actually become planar. And then, of course, we'd have to ask ourselves the question, why? Interesting problem we're not going to do now, but could be done. So that's kind of an illustration of a system that if all of the atoms were to become planar, it would be anti-aromatic. So those two atoms, one of those two atoms is going to say, no, I'm just going to stay sp3 hybridized. And if it stays sp3 hybridized, you're going to have 5 of the atoms in a plane, and then you're going to have one drop down or up. Does that kind of make sense? So again, I have some practice problems somewhere that I'll find and I can put in the folder so you can kind of go through. Because if I ask you these questions, that's kind of what I'm going to ask. Is it anti-aromatic? Is it aromatic, non-aromatic, or anti-aromatic? And some molecules just don't have a choice. They have to be anti-aromatic. And if we go back to our original list here, one of the ones that was definitely anti-aromatic was the cyclobutadiene, because this has no choice. All the atoms are starting out sp2 hybridized. And the cyclooctatetraene would also be anti-aromatic, given its structure, except it isn't. It basically contorts out of the ring so that it's not anti-aromatic. It has the flexibility to do that. Cyclobutadiene doesn't. Okay, so for heterocyclic compounds, this choice is how they proceed. Now, I do want to talk about bases here for a minute. So, for nitrogen compounds, what does it take to be a base? Something like NH3 is a base. It'll pick up a proton very easily, and it'll form NH4+. What the nitrogen needs in order to be a base is it needs a free pair of electrons that can bond an H+. So oftentimes we'll talk about, is this nitrogen basic or not? Particularly nitrogens that are in potentially aromatic systems. And I'll give you 2 examples of where it is and where it isn't. So pyridine. Pyridine is not a particularly great compound. It's a reproductive hazard. It's not something that we use, although it is in our reagents like PCC that oxidizes a primary alcohol to an aldehyde. That's what the P stands for, is pyridinium. So pyridine is a very strong base. Why? Because its lone pair is not part of the aromatic system. Its lone pair is outside of the aromatic system. And so it's free to grab a proton. What about pyrrole? Well, if I looked at pyrrole, I would say, yes, that nitrogen has a lone pair, but then I have to ask myself, can that lone pair be used to bond to an H+? And if that lone pair is part of the pi system that's making the system aromatic, it is not available to bond a proton. So in this case, pyridine is basic. Pyrrole is not basic. Because that lone pair of the nitrogen is part of the aromatic system, and once it becomes part of the aromatic system, it cannot grab an H+. Does that make sense to everybody? So then, this is honestly the first time anybody said that this is a nitrogenous base. So I have to ask myself, what is it that that term base means? Because it may mean, well, it could be the base as in terms of the base pair of the DNA in biology speak. But in chemistry, when you call something a base, it means it's a base. It can pick up a proton. And so from the chemistry standpoint, calling this a nitrogenous base would not be correct. Because we've already established, right, that this lone pair has to be part of the aromatic system. Or would be part of the aromatic system. So this nitrogen wouldn't be it's not going to be basic. It's not going to bond an H+, because its lone pair is part of the aromatic system. So it's not available. Okay. So I think in that terms, they're talking about it being a base pair. And base does not mean base. It does not mean the ability to pick up a proton. Up here, part of the way, just sort of an aside, part of the way I would determine which atom is not planar would be whichever one would pick up a proton. If I was to add acid to this system, would the proton go to the nitrogen or would it go to the oxygen? And that would tell me which system is planar, because that would not pick up the proton, although this oxygen could pick up the proton on the end. So sometimes when we talk about nitrogens being basic or not basic, that's what we're talking about. We're talking about, does that nitrogen have a lone pair that it can use to bond an H+? If the lone pair is not part of the aromatic system, in other words, it's outside of the ring, it will be basic. If that lone pair is tied up in the ring system, it will not be basic. So sometimes you'll hear people ask that question, is that truly a base or not? Everybody kind of okay with that too? So we have to determine for heterocycles whether the nitrogen, number one, it's got to be sp2 to be aromatic, and if it is, it's got to then put a lone pair into the aromatic system. But it'll only do that to become aromatic. It won't do that to become anti-aromatic. All right, everybody okay with that? So as I said, I'll put some practice problems, and you also see practice problems of that on the older exams. So there's plenty of older exam questions. Some of them are probably similar because there's only so many questions I can ask over, I don't know, the 10 years or 15 years or 18 years of exams that I have online, which I've got to cut down because there's too many questions. Our last thing to talk about with aromatics is very similar in terms of ions. Now, when we talk about aromatic ions, the first thing is like, well, how can an ion be super stable? Because we know that an ion itself means that it's not a neutral charge, and anything that's super stable wants to be neutral. So again, super stable compared to another, let's say, cation. So let's, for instance, take this. Let's take the cyclopropyl cation. Put it at the top here. So in order to determine whether it's ion or whether it's aromatic, I now have to realize that a carbocation is always sp2 hybridized. I did that a few minutes ago, but a carbocation is always sp2 hybridized. A carbanion, well, I did that one a few minutes ago. That could be either. Could be either sp3 or sp2. But a carbocation has no choice. It's sp2. So when I look at this cyclopropyl or cyclopropyl carbocation, all three atoms are sp2 hybridized. How many total pi electrons? 2. How many in the carbon? 0, because it's a carbocation. So there's 2 pi electrons here. Does that fit the rule? Does that fit Huckel's rule? Yes. So this is an aromatic cation. What does that mean? Well, what that means is compared to other allylic carbocations, this one is far more stable than your run-of-the-mill, non-aromatic, secondary allylic carbocations. And you might then say, oh, how do you know that? And then I go back and I remember a whole bunch of things, like Hammond's postulate, Arrhenius equation, and I say, I'm going to test this. So I get myself a secondary allylic secondary allylic chloride that can go ahead and form a secondary allylic carbocation. And then I make myself a cyclopropyl chloride, so that when it loses its chloride, it forms that carbocation. And then I say, you know, this is the first step to a what kind of mechanism? It'd be an SN1 because I'm forming a carbocation. So both of these reactions are undergoing SN1. And if it is true that this is aromatic, what should happen? Jacob?
You'll have a slower rate.
It'll form that carbocation faster. Because it's more stable than your regular run-of-the-mill secondary allylic carbocation. So if I measured the rates of this reaction, I would find this one should form more faster, even though that's not a real word. That's not a real phrase. It should be faster, but it should be really fast. Okay. Because the system I'm forming is aromatic. So it's not that, this is just going to kind of lie around there forever and not react. That's not true. But comparing its stability to something that isn't aromatic, it's going to be much more stable. So that would be our carbocation. And so this one, so that cyclopropenyl carbocation, I don't know how much work's been done with that, if any. But there are some other ones, though, that we use all the time. Oh, look, it's our friend the Trapillomyne for some of us. Where have we seen the Trapillomyne before? For those of you that have seen it. In lab, in spectroscopy, mass spectrometry, actually, because when you form a benzylic carbocation, which was formed by taking any alkyl benzene and chopping it off to form this carbocation, that carbocation rearranges itself to form a tropyliumine. They both have the same molecular weight, which was 91. So in your mass spectrum, if you think you have a benzene ring and you think it has an alkyl group attached to it, you always look for the peak at 91, because the peak at 91 tells you that it's either the tropyliumine or the benzylic carbocation. But the reason the tropyliumine is formed in mass spectrometry is because it's aromatic and it's very stable. How you get from the benzylic to the tropyliumine, there's a lot of debate on that. I tried to make up a mechanism in one class period, and then it didn't go well. Because I kind of got stuck and had to make some steps that didn't quite make any sense. Then I went and I looked up what the real mechanism was, and there wasn't one. People were arguing about this versus this, and so I will never make that mistake again of trying to invent the mechanism in class. Silent stable. Here's an anion called the cyclopentadienyl anion. And so in the cyclopentadienyl anion, I have a carbon with 2 lone pairs. That's what makes it a C-. So in other words, I removed a hydrogen. And for that cyclopentadienyl anion, if the carbon becomes sp2 hybridized, much like the nitrogen and oxygen that we've seen, then that lone pair gets kicked into, actually, there's just one lone pair, because there's a hydrogen here. That lone pair gets kicked into the p orbital. We now have 2, 4, 6, and we now have an aromatic system. Cyclopentadienyl anions are actually quite easy to make. Sometimes you will see them. The most famous case is that they like to be sandwiched. They form on sandwich compounds, which you've got 2 cyclopentadienyl anions with an iron in between it. Those are called ferrocene molecules. But you can do different metals, and so those are actually very useful. So again, that anion would be formed faster than normal anions. Okay, so that's aromaticity, and that's where we'll stop. On Wednesday, then, if you have questions, bring them to class. We'll go over them. Otherwise,